an idea of what the collaboration team has done, we've put together a work plan for this upcoming year, motivated strongly by the rich discussions that we've had surrounding the conditions in Bering Sea. So we've come up with three focuses or foci of themes, and we'd like to revisit these periodically throughout the year. So the first one being sea ice sickness and the sea ice conditions in the Bering, Chukchi, and Beaufort Sea, and today's meeting is to kick off this theme. And we'll be revisiting this in October later this year. The second theme is harmful algal blooms, and then the third theme is shore-fast ice. So the idea is that we'll have these iterative conversations, and we're aiming to engage a diverse group of people who will use IARPC as an opportunity to network and share what they've been working on. So today we have two excellent speakers, really looking forward to hearing about their work. The first up is Nathan Kettle, and his presentation is on the co-producing sea ice tools to improve situational awareness and crisis response in the Arctic. I think I'll just pass it to you, Nathan, so you can get started and you can explain more about your project. Does that sound good?
That sounds great. Thanks for the introduction, Melinda.
Thank you.
The presentation up?
Yes, it is.
Excellent. Well, thank you again for the opportunity to provide an update on a project that seeks to develop some prototype sea ice hazard tools to address situational awareness and crisis response in the Arctic, which is done via a collaborative effort among researchers, service providers, as well as those individuals that would be making decisions that are sensitive to sea ice conditions. So this work is being done by myself, as well as with Doctors Andy Mahoney, Hayo Aiken, and Lawson Brigham at the University of Alaska Fairbanks. For a brief little background and context, as many of you are aware, improving situational awareness has become a key element in both supporting planning as well as emergency responses in the Arctic. However, there can be several challenges to being able to provide the support given the rural and at times remote location of where these hazards may occur, as well as the limited infrastructure and availability that may be able to brought to bear on these decisions, and the importance of Arctic system science and how those observations can be brought into decision support. There's also a need to improve these tools in a way that better serves operators, and this includes both better understanding the data flows that can occur between individuals that would use the information, those that would be producing and disseminating the information, automating procedures from observations to notifications for decision support, as well as understanding key decision thresholds, or what are those environmental parameters that are once reached may trigger a change in decision, such as a go or no-go decision. We also know from a rather extensive literature and knowledge co-production that increasing the interactions among researchers, service providers, and decision makers can increase the usability of the decision. It can create information that is perceived to be more legitimate, perceived to be more trustworthy and relevant. And finally, within the Arctic, utilizing existing observations is a critical piece, as it can increase the cost effectiveness of the decision support that's provided. Within this context, our project team sought to develop some prototype sea ice hazard tools, and we based this research in Utqiagvik, formerly Barrow, and we selected this for a number of reasons. One, there are multiple marine operators, responders, and subsistence hunters in the region, as well as in the past there's been multiple sea ice hazards. We'll be talking about three in particular: convergence, breakout, and high-speed events. There's also a natural choke point of activity which can concentrate marine activity within this region, and there's several long-term data sets that can be leveraged to increase the cost effectiveness of developing decision support in this region. For these decision support tools that we're developing, we're basing them off of the Coastal Sea Ice Radar System that has been run by Dr. Andy Mahoney in the Geophysical Institute at the University of Alaska Fairbanks. This radar is operated in Utqiagvik, and in its current iteration has been operated since 2006. So we have around 13 years of data to draw on here. The radar feed is about 6 nautical miles, and images are taken about every 4 to 5 minutes. So we have a relatively high temporal frequency of these data to analyze. And then images are sent about every in packages. About every 4 to 5 images are sent about every 20 minutes to UAF for analysis. For our approach to develop these tools, we developed a multi-phased approach, which began with preliminary tool development. So we began by assessing the decision context. So what are the decision needs, constraints, and opportunities to developing sea ice hazard tools among those decision makers and service providers that would be providing the information? Second, we are going to be developing early warning systems for these hazards. So 3 prototypes based on the analysis of historical data, and then defining the hazard notification formats and procedures. Once those preliminary tools were developed, we sought stakeholder feedback and optimized the tools based on their feedback, and then engaged in some evaluation and outreach activities. So to begin briefly, we began with the assessment of the decision context, which had 2 different components. One was a literature review, and the next was conducting some semi-structured interviews. The literature review identified 45 documents related to sea ice information needs, as well as assessments of information use. That information was synthesized to be able to help us scope and develop a series of interviews that were conducted among the service providers that we'd be working with, including the National Weather Service, the Weather Forecasting Office in Fairbanks, and the Alaska Sea Ice Program, as well as NOAA's Arctic IRMA. We also identified and interviewed marine operators, U.S. Coast Guard, responders, including local search and rescue, as well as subsistence hunters within the region. We also interviewed researchers that were involved within this radar system. We used from these interviews, so here are some of the key pieces that emerged as it relates to the development of the tool. One, that some thresholds were identified. So at what point did people want to be notified that certain conditions existed? And for the specific sea ice hazards, they were interested if the sea ice was at least 0.2 square kilometers in size. That would be a big enough of an area that they'd be interested in. If the ice was moving at 0.6 meters per second. And for breakout events, was it at least stable for 7 days before breaking out? And I'll be illustrating how we incorporated those thresholds into the development of our prototype tools. Additionally, that awareness and use of the UAF radar, Arctic IRMA, and NWS products did vary quite a bit among the different groups. For example, the U.S. Coast Guard uses some of the National Weather Service products and Arctic IRMA within their daily briefings within search and rescue, but we're not familiar with the UAF radar, although they are very interested in the high resolution, both spatially and temporally, that was available through it. In contrast, the subsistence hunters were very familiar with the UAF radar and indeed were given some of those images during a search and rescue event that happened a few years ago, but were less familiar with Arctic IRMA. Through our discussions with the Alaska Sea Ice Program, we had identified that incorporating observations from this system within the Sea Ice Advisory product was the most suitable avenue, so utilizing existing products. The second component was to be able to begin developing some prototypes of the sea ice hazard tool. So first we looked through the historical data to be able to understand, can we identify 3 different types of hazardous events from these data? And what we have on the horizontal axis is the month and year. The vertical axis is the frequency of events, and that gray area represents days where there's data. So clearly there are some times where the data is not available as the radar is down, which is certainly a challenge to the reliability of such decision support tools that we'd be providing. It did illustrate that we could identify both convergence and breakout events. The high-speed events were not included in here. So within the 120 calendar months, we were able to identify 245 convergence events and 147 breakout events. Here are the illustrations of the 3 different types of sea ice hazard events that we'd be creating our tools for. On the far left, we have the breakout events. So in the green represents land, the black is the water, and the ice clearly illustrates the breakout that's happening. The red arrows just are the vectors helping to describe where the sea ice is moving. That would be a breakout event. Here's the high speed event. Apologies for the resolution. That is lost. Here we go. And if we look in the upper left part of the screen is where you start seeing the ice start moving at a much higher speed. And in this instance, it reached that minimum threshold of 0.6 meters per second and was thus deemed a high-speed event. And the final one is the sea ice convergence event. The white speckle around the center of the radar is choppy waters, and we'll start seeing the ice convergence in the upper left part of the screen as the sea ice begins to move shoreward. We'll also notice as the sea ice gets really close to shore that you'll see a boat that moves from the upper right to the lower left part of the screen, a rather bright white dot that shoots through. That's a boat that's trying to clear through, and it should be coming through right in here pretty soon. There it is, a boat trying to come through before the convergence event. So clearly, these three types of hazards present a hazard to multiple marine operators within the region. So the next part of it was if we can detect these events based on the analysis of historical data, can we develop procedures to automate the detection of these events from the velocity fields? Here's an illustration of the high velocity events. So we'll click the event, and we'll see the timeline of events that happens at around 2044. The ice begins to move at a higher velocity, yet we didn't want to just have an alert that the high velocity had been reached, but that we wanted it needed to move for at least 2 hours at that high speed before that threshold was reached. So there's a delay of about 2 hours and 20 minutes. That 20 minutes has to do with the sending of packages of the images from Utqiagvik to UAF. And then shortly thereafter, notification of that high velocity event could be sent to the National Weather Service Alaska Sea Ice Program for their review. Here's an example of the convergence event. So again, as we'll see from the upper left, the sea ice will begin to move shoreward. So around 1703, the radar detects that the sea ice is starting to become moving visible and moving shoreward. 2 hours later, it's detected, and then almost immediately then notification that the convergence event happened was sent to the NWS. It's worth saying for accuracy on this, it's about a 15 to 20% false alarm. We're working to currently reduce the false alarm rate. So we've identified all the events, but there are times that we've identified event, but by visually looking at it, it actually doesn't look like it's occurring. Let me go back one screen here. So if we do this next event, here's an example of all three events happening at the same time that begins with the convergence event that we haven't looked at yet. In this instance, there's not a delay in 20 minutes, or there's just a delay of 20 minutes before when the breakout event happens, and then when the data are transmitted to UAF and that breakout event would be detected. We then see that the ice starts moving shoreward, and then 2 hours later, for that minimum threshold of moving towards the shore, the convergence event was detected. And then we also see a high speed event and starts to occur. So clearly a dynamic environment with multiple types of hazards. So what does this mean within a broader context of providing information systems? Here's a figure that illustrates more of this hazard communication framework for the delivery of information. And if we begin on the left-hand side of the screen, we see that we have the radar observations, which are providing snapshots about every 4 to 5 minutes, and then those packages are sent about every 20 minutes to UAF. And multiple processing steps are occurring, including georeferencing, image annotation and sequencing, as well as several calculations of the ice velocity and divergence and detection of ice thresholds. Additionally, several interim products are developed that are both web-ready and GIS-ready. And from here, a couple different pathways can be taken to integrate these Arctic system science observations into a decision support framework. On the top, we have the example of the notifications of these events for breakout, convergence, and high-speed events that could be sent to the National Weather Service Alaska Sea Ice Program for their review and for potential inclusion as an observation within the existing sea ice advisory product. Secondly, there's the potential to integrate this within NOAA's Arctic IRMA program. So not totally reinventing the wheel, but utilizing dissemination outlets that are currently being used by operators with NOAA's Arctic IRMA that is frequently used by search and rescue within the U.S. Coast Guard. We have not implemented and actually done this yet as the radar is currently down, but we've had several discussions with Arctic IRMA to be able to determine how best we can get these near real-time data within that operating environment. We're also exploring additional opportunities to be able to get information sent out at a higher frequency. For example, we've begun to explore some opportunities in working with AOS, the Alaska Ocean Observing System, to be able to get that information up online and potentially send out notifications via email or even texts that there have been a change in the condition. So in conclusion, this work suggests the importance of Arctic system science observations in their use in decision support tools and in meeting decisions maker needs in the Arctic. At the same time, there are several challenges to doing this, especially given the challenges of operating and maintaining near real-time data in the Arctic, as several of you are aware. These radar systems, although they provide near real-time data, or they require a constant source of power and internet connections, locations that are easily accessible to be able to maintain and fix any of the problems that may emerge. And therefore, I'd suggest that innovative partnerships are going to play a critical piece in utilizing Arctic system science observations for decision support. In the example of the system we're using here, the local internet company has provided internet access at no cost. ASRC has gratefully let us install a radar on top of their building to be able to decrease the costs. And although this work has focused on Utqiagvik, clearly there is a need across the Arctic for such decision support tools. Within March, a man was rescued from drifting sea ice out in Nome, and Nome itself could present an ideal location to install additional radars such as this, as there's a National Weather Service service office there. There's a population there that would be able to fix the radar without having to fly an individual from the research team up there. There's a constant supply of power and internet availability there. So clearly there's opportunities to install radars such as this in a few locations across the Arctic. I would like to acknowledge several individuals and organizations for their support of this work, including funding from the Arctic Domain Awareness Center, as well as the Alaska RESA program, the Alaska Center for Climate Assessment and Policy, or ACAP, as well as several of our collaborators and interviewees from the U.S. Coast Guard, the National Weather Service, subsistence hunters, and local search and rescue up in Utqiagvik. So with that, thank you for an opportunity to provide a summary of the project.
Thank you very much, Nathan. That was an excellent presentation. I'd like to open it up to questions if anyone would like to ask Nathan about this work. Okay, I have questions, so I'll start things off. So you mentioned that this is a really, really nice site and it's a location. Are there other locations collecting similar information, or is this really the one big thing that's happening in Utqiagvik?
So Dr. Andy Mahoney is in a much better position to answer all the questions on all the Arctic system science observations. I'm a scientist by training, but I can say they have tried to install radar sites at other locations, and they have faced several challenges in being able to maintain and keep those systems up and running. And Utqiagvik has been one of the easiest sites for it to be able to be maintained. But even at that, the radar is currently down, and trying to maintain sources of funding to continue decision support after an individual grant for Arctic system science has been completed has been a challenge. One of the interesting pieces that emerged was both the U.S. Coast Guard and subsistence hunters were interested in having a radar installed out at Point Barrow, and they're also interested in having radars that have a further range. Having one installed out at Point Barrow, although very useful and a high level of interest, would certainly present several logistical challenges trying to get a constant source of power, internet connectivity, and even a high building to be able to install the radar. And I think, again, opportunities to be able to increase how we can do this. Partnering, I think DOE possibly has a radar site out there, and possibly trying to find ways to partner with some of these other organizations to provide more consistent and reliable observations will certainly be a key piece.
Great, thank you. Are there any other questions?
This is Florence. I have a quick question. You've used the radar as a case study here for how you did co-production of decision support tools. And I'm wondering, is there any other sort of ripe for the picking application you could see for your method in Alaska or anywhere else?
Is that question specific to radar or more broad?
No, it's anything.
Right, that's a great question. And I could even open that up more broadly to the Sea Ice collaboration teams, as this is my first project with Sea Ice, and I would love any ideas that folks have based on your broader extensive knowledge with Sea Ice that you could see would be ripe for co-production.
Right, I think that's a really good point to keep a discussion going on, and we should definitely revisit that in these future meetings because it's a big topic and I think there are paths forward with that. But yeah, it would be much better to bring in the whole community in on this.
I can say it's my understanding that the National Weather Service is very interested in trying to understand how we can leverage these other existing observations in order to be able to enhance decision support operations that they have. So clearly there is an interest both in those that are providing information as well as those that would be using these information and data for their sea ice sensitive decisions.
Right. Are there any other questions for Nathan? I have one last quick one before we move on to Sinead's presentation. So you were talking about these thresholds that were really important to have information on. So the size of the flows, the speed, and what was the other one? I forget the third. But there wasn't thickness, and I'm wondering, is sea ice thickness information that could be used in the future, given that ISAT-2 has a relatively high-resolution footprint? Is that information that's useful at this type of application?
Clearly, stakeholders are interested in several environmental variables. Sea ice is one of those, and we're not able to include sea ice thickness in these tools, but there is also an interest in currents. There's also an interest in wind speed and finding ways that you can integrate all of these observations into a single location to be able to access that information is clearly of interest. So I would say finding ways to include sea ice thickness in this application would be very interesting for the stakeholders.
Great, thank you so much. Any last questions before we move on? Okay, well, thank you very much, Nathan. Sinead, how about we switch it over to you? And Sinead will be talking about ISAT-2 status update, incorporating photon-counting altimetry in your sea ice research.
Okay, thanks, Melinda. I'm not able to share my screen right now. Let me see if I can try that. Okay. That should be working now.
Yep.
Okay, great. Well, thank you again for inviting me to present to the Sea Ice collaboration team. I really appreciate that. And hopefully you can see my screen okay.
Yep.
Great, thank you. So I'm just going to give a brief overview of the ISAT-2 mission, just a status update, and hopefully describe some ways or spark some ideas in your own minds about how you might utilize the data in your own research. I wanted to acknowledge the ISAT-2 science team and also the NOAA Laboratory for Satellite Altimetry Sea Ice team in this work. So just moving on. So basically the data went public just at the end of May, and hopefully plenty of people on the call today have already started looking at the data. But just in case, I thought I'd put in a couple of slides to sort of navigate you through how to access the data and little things to look out for as you're navigating the data set. So all of the data are held at the National Snow and Ice Data Centre. And I think that Walt and Florence are on the call, and they can certainly speak to the facilities and tools that are available at the National Snow and Ice Data Centre, if there are any questions about that at the end. But basically so this is the ISAT-2 landing page, the home page for the mission. And I'll draw your attention to a couple of things that I've highlighted in magenta. So hopefully you can see those. If at any time you're interested or have questions about the product, or there's some issue that you've encountered, definitely look out for the support button, which I believe is a green button on the bottom right of every page. I've tried using that myself a few times recently. It works really well. And the folks at NSIDC are really keen on getting any user feedback on the data sets or information about how people are using the data. So feel free to drop a line through that web link. So then to move on, I've highlighted a number of different levels of data that the sea ice team members may be interested in using. So if I click to the next slide, this is the wiring diagram of how the different levels of data work. So basically I'm highlighting level 2, level 3A and level 3B data. So the level 2 data product is the so-called photon cloud data. That would be equivalent to the full waveform data that you might be used to getting from a radar altimeter such as Cryosat-2. These data are, so the product is called ATL03, and that contains every single photon in the cloud plus the geolocation for those photons and the height associated with those photons. So it includes both the signal photons from the surface and photons from just background light. The instrument on ISAT-2 is called the Advanced Topographic Laser Altimeter System, and that is a laser that detects at 532 nanometers, so green light. So just going back to the ATL03 product, it's quite a large product. So, you know, that's kind of for detailed use. If you're just looking at one particular segment of an orbit, for example, for calibration and validation analysis, or very, very high resolution analysis of a particular region. Probably of more interest to the sea ice collaboration team here are the sea ice products themselves, and they are ATL07, which is the sea ice elevation product, and ATL10, which is the sea ice freeboard product, and I'll be showing more analysis of that in the next few slides. So those are the data sets that are currently available. And then coming in the future, we'll be uploading or making available a gridded data product that's just currently under development. And I think the expectation is to have that released through NSIDC in the fall. So that will be a sea ice data set on the regular 25-kilometer EASE-2 grid. So that will be of use to many of the people on the call, I think, as well. And some just initial information about the initial data release. The satellite was launched in September, started collecting data on the 14th of October, 2018, so last fall. And the data are there available at NSIDC from the 14th of October through to the 23rd of February at the moment. The next batch of data is just going live today here in our operational system at NASA through the Science Computing Facility, and it then takes a few weeks for it to be validated and quality assessed by the science team, and then it gets transferred to NSIDC. So you'll have access to that sometime in July, probably sooner in July than the end of July, but we'll see. So stand by for that. So that will include the data for the end of the winter season in the Arctic. So just a quick overview of it's a satellite mission, so just talk about the coverage really briefly. So ISAT-2 provides coverage of both poles to 88 degrees north or south. For the purposes of this talk, I'm just focusing on the Arctic since it's an IARPC presentation. And so I just wanted to show the coverage over the Arctic Ocean simply after 4 days or 61 orbits. That's a subcycle of the ISAT-2 mission. And you get complete coverage after 4 days at that type of resolution, which is obviously quite variable depending on where in the Arctic you're interested. And then after 1 month or approximately 29 days, you'll get much denser coverage. This then builds up to a 91-day repeat orbit, and I didn't show that because it just looks like a red, all the lines merged together, so you wouldn't see very much detail. But basically, the satellite is in a 91-day exact repeat orbit, so every 91 days it profiles the exact same track on the Earth's surface, and that is to obtain 4 measurements of every point on the Earth's surface per year for a seasonal evaluation of seasonal changes. But for our purposes, looking at the Arctic Ocean, I think people will be interested in data at a 1 week resolution or maybe at a 1 month resolution. So that's what the coverage will be. So then just very briefly to look at the landing page for the data access. If you're interested in the sea ice freeboard product, for example, that, as I mentioned, that's ATL10. And so if you click on that link, that it'll take you to a page like this, and just a couple of things to look out for. There's a tab for downloading the data and various ways and tools to obtain the data itself in HDF5 format. There's also a user guide, which is useful. It's a bit like buying IKEA furniture and trying to build the furniture without reading the manual. I wouldn't recommend it. So definitely take a look at the user guide, and that will help, for example, to explain things like the file naming convention. So this is an example of a sea ice freeboard product file. As I said, it's HDF5 format, and there are various things in the file format that identify it. For example, the 01 here at the very beginning of the file tells you that it's the northern hemisphere. If it has a 02, then that is the southern hemisphere. So that's a quick way to identify Arctic versus Southern Ocean sea ice freeboard data files. Okay, I'm just going to move through this pretty quickly. It's all pretty straightforward. This is just an example of how you can actually access the data. So this is through Earth Data Search, and you can get browse products for the particular track, and it'll give you the time and date of that track and show you on the map where that track is located on the Earth's surface. And then you can go ahead and download the data over here using an FTP type system, a kind of a pull system, or I guess it's HTTPS. And there's a little toolbar at the bottom that shows you the availability of the data in time. And so that green line will continue to grow into the future as more data become available. And then just to say that in case anybody's not really familiar with the ISAT-2 system, it's as I said, it's a laser altimeter, and the laser beam is a green laser. It's split into 6 beams. It's one laser, but split into 6 beams on the Earth's surface. And these are arranged in pairs of beams. Each pair has a strong beam and a weak beam. And that is, the strong and weak beam are there because over very bright surfaces, specular surfaces, such as very, very bright leads or melt ponds, for example, in the sea ice cover, we receive a lot of energy back from those surfaces. So we have a weak beam so that the detector doesn't get saturated in a situation like that. The strong beam is then for obtaining measurements over darker surfaces, such as the ocean. The open ocean is quite a dark surface for the laser. So that's the reason for the strong and weak beam combination. And then each of these beam pairs is separated by about 3 kilometers across track. And so the beam pairs actually measure different topography to each other, depending on the variability of the topography in that at that length scale. So it's kind of interesting to compare the data from the different beams. And then in our nomenclature in the file naming convention and within the HDF5 file names, within the HDF5 files themselves in the data structure, the data are arranged by beam name. And so we talk about ground track GT, 1L for left or GT1R for right. So there's a 1, a 2, and a 3, a weak and a strong beam for each ground track. Hopefully this is all making sense. And then just to complicate matters even further, sometimes we flip the satellite. So it still has 6 beams in the along track direction, but the beam that used to be a weak beam now becomes a strong beam. And that has already occurred, and we will flip the satellite probably twice per year. And that's to do with the solar angle of the solar energy on the solar arrays to keep the spacecraft powered. So hopefully those are little tidbits of information that will be helpful as you dive into the data. And the webpage, the presentation is available on the IARPC webpage so that you can look at these notes later. If you've got any questions, don't hesitate to contact me or contact NSIDC. So then just briefly to look at the actual data itself. So this is an example pretty soon after launch of a track that covers the Beaufort Sea, the southeastern corner of the Beaufort Sea, just south of Banks Island, southwest of Banks Island. And at that time in October, there was a pretty broken up area of multi-year ice in this region, as shown here in this SAR image of the sea ice surface, of the ocean surface, I should say. So you can see all of these bright multi-year sea ice flows, rough sea ice flows, and then in between those, it's a darker surface. Those are actually refrozen leads or just new ice forming basically in the Beaufort Sea at this time of the year. And then you can see that the beams, the 3 major beams, the strong beams, are kind of profiling the surface parallel to each other as the satellite orbits over the Arctic. And then you can see the detail here on the right-hand side of that surface profile. So this is a plot of elevation versus time, or in fact, the freeboard of the sea ice versus latitude, distance. And I include this this was a very early example or result from the mission. And we could immediately see the details, the high resolution, high fidelity measurements that ISAT-2 will be providing over the sea ice surface. So you can identify areas like basically completely open leads, areas where some ice is being formed, new thin sea ice, level ice, pressure ridges pop out, rough sea ice flows. All the detail is there. And the system will operate throughout the year. So you'll have access to, as I said, the photon cloud data for the from the mission for the whole year, or the sea ice elevation in the ATL-07 product, for example, will give you just the height of the sea ice in the along track direction. So it's really detailed, and there's so much information in there. It's fascinating to look at. Every single track is interesting to me. Of course, there are some dropouts because of clouds. It doesn't operate in extremely thick cloudy situations. We don't get, the laser beam doesn't get returned to the detector. So we do suffer some dropouts at certain times of the year, but in general, we've been getting really good coverage over the sea ice right up until the present day. I was just looking at data from 2 days ago over the weekend, and we're already seeing surface melt on the sea ice. So just to kind of look at the freeboard product itself, I wanted to talk a little bit about, if I have time, to talk a little bit about the conditions in the last winter. So here I'm showing ISAT-2 freeboard in the center of the slide, and this is the snow plus ice freeboard. Because it's a laser altimeter, it's interacting with the snow-ice interface. And so the scattering, the major scattering, is from that surface. I compare that on the right-hand side to the Cryosat-2 sea ice freeboard, and that is a radar altimeter. And that is predominantly scattering from the snow-ice interface. So you can see the differences in the volume, or the magnitude, I should say, of the freeboard, but you can also see the comparisons in terms of the distribution of the thicker freeboards, the spatial scale, and the gradient of the detail, the gradient of the thicker to thinner seasonal sea ice here in the Chukchi Sea and in the Eastern Arctic Ocean as well. And just for comparison, I put together the the sea ice, the multi-year ice extent that we derive at NOAA from ASCAT. So that's a radar scatterometer. And you can see the consistency in the signal between all three systems, completely independent systems using different technology, obtaining very, very consistent and complementary information about the thickness of the sea ice cover. So if we can just look at the seasonal, hopefully, sorry. This is an animation, hopefully it'll play. Yes, this is the seasonal evolution of the sea ice during the last winter. So this is winter 2018 into 2019, and we're just looping through November, December, January, February, and March. And those are the data files that we've got available to us right now. And you can see how in the ISAT data on the left-hand side, the tail of thicker ice that extends into the southern Beaufort Sea from the Canadian Arctic, the central Arctic and Canadian basin, the Beaufort Gyre and probably southerly winds have pushed that along the sort of parallel to the coast of Alaska and then pushing further north as the season went on. So it's really interesting now that we can see the seasonal evolution by monitoring the ISAT-2 data every month of the year. And again, I just, showing Cryosat-2 here on the right-hand side for comparison as to its capabilities. And then if we combine those together, as I mentioned, that the penetration of these wavelengths into the snow cover on the sea ice, differences in penetration give us some information about snow depth. And so if we difference these freeboards, we get a parameter that we're calling LARA freeboard. That's laser altimeter, radar altimeter freeboard, and that's a proxy for snow depth. And I just show this as a quick example here of the differences. Nothing fancy has been done here. This is just averaging the data at 30 kilometers and differencing it, taking into account the speed of light propagation through a snowpack. And you can see that, well, first of all, the magnitude is probably a little bit thin in terms of the absolute snow depth, but the magnitude of the freeboard is definitely in the right direction. It's not negative, which is a relief. And there's definitely a gradient here that we would expect. It's consistent with the deeper snow on multi-year sea ice and thinner snow on the seasonal sea ice. But as I said, this is preliminary, it's not validated as yet. And we will be, we're currently conducting validations of this using airborne data that was collected during the March and April time period of this spring. So here we have a set of ice bridge flight lines. We conducted a number of surveys. Every flight survey was done from Thule, Greenland this year. Every survey underflew a satellite. So there were 4 underflights of ISAT-2, but we also underflew Cryosat-2 and Sentinel-3, which is the Copernicus radar altimeter currently in operation over the Arctic. In addition, the Alfred Wegener Institute had their Icebird campaign, and I'm just showing one example here where the group underflew an ISAT-2 orbit as well. And there were some additional underflights of ISAT-2 up here in north of Greenland and on the Greenland ice sheet that were conducted by the European Space Agency Cryovex campaign. So just to say that we're looking forward to analyzing the validation data, and just an example of this, just to show you that this is what the raw ISAT-2 data looks like for a particular underflight, the photon cloud data. And stand by for further updates on this throughout the year from us. We'll be presenting at the IGS meeting in Canada in August, and look forward to sharing further results with you then. Thank you very much.
Great, thank you so much, Sinead. I'd like to open it up for questions. We have 4 minutes left, and after questions, I'd like to open it up to another discussion for what the follow-on meeting should be. So any questions for Sinead?
Yeah, this is Rick. Hey, Sinead.
Hi.
Have you had a chance to look at the freeboard data in the Antarctic yet?
Thanks, Rick. I knew somebody would ask that question. I'm going to blame the upload limitation of 50 megs to the IARPC website. I had some Antarctic slides and I had to delete them because the file was too big. But yeah, sure thing. We do have freeboard data from the Antarctic. It's available. Just go for ATL 10 products and you'll be looking for the 02 data product. So it's ATL 10-02, and that's the Southern Hemisphere Sea Ice Freeboard. Yeah, it looks good. Taking a quick look at it. There's lots of icebergs, of course, down there, so you've got to watch out for those. And I'll have a slide about that at the IGS meeting, or I should say a poster on that Southern Ocean Sea Ice at the IGS meeting. Thanks for your question, Rick.
Thank you.
Great. Any other questions for Sinead? Okay, well, I have a question that I think links back to Nathan's talk. So Sinead, what you're presenting is pretty much like a product for research and some operational activities. And Nathan's was really focused on operational support. Is there an opportunity for a link between these two products, or a link between these two efforts to using ISAT-2 information and sea ice thickness information for something that supports ADAX efforts?
Yeah, exactly, Melinda, definitely. And I think that's a really important topic that may again provide for discussions at future meetings. At the moment, there's a latency of about 45 days. Well, at the moment, the latency is not really reasonable because the data are just starting to be uploaded through the NSIDC. But when the data start flowing regularly, there's a latency of about 45 days associated with the freeboard data, but the photon cloud data will be available at a lower latency, as in sooner to the public. So there are possibilities to use the data straight away in an operational setting. I think probably the best approach, or the most interesting use of the data, would be in initializing forecast models. So anybody who's doing a sea ice forecast, such as Rick Allard's group at NRL, can utilize the ISAT-2 information to initialize or seed their model with the freeboard information, and then the model can then be used to project forward in time the likely location and thickness of the sea ice in particular regions. So I definitely think that that's a possibility for future research and growth in the very near term.
Great, thank you so much. Are there any other questions before we wrap up? All right, well, everyone, thank you very much for attending, and thank you, Nathan and Sinead, for giving us this presentation. So I've really enjoyed them, and we'll be following up with you. So thank you.
Thanks so much.
Thanks.
Thanks, everybody.
Thank you.
Thank you. Bye-bye.